Hello everyone. In the previous video, we had derived the equation of the Elastica as well as the boundary conditions, which I have written down here. And today we are going to see an application of this theory towards the same example problem that we had considered earlier using the approximate theory. So this is that example. It's exactly the same diagram except that I have changed the coordinate system. Earlier, the x was directed along the same direction along which I have written this S here, and the Z was perpendicular to it. Okay, now if you just compare with the previous page at which I had ended the previous video, you will see that there's a slight difference in the way that the boundary conditions are written here. You see, I had written here this as at x equal to 0 and at x equal to L, these things either eid theta ds equal to 0 or theta is specified, but in reality this should have been written as s equal to 0 and s equal to L. So this is S and this is S. Okay, so that's a bit of a correction, but it is not really a correction in the sense that in the undeformed configuration of the beam, that is in the pre-buckling stage, it is indeed true that X, what I had previously written, and the S, which I am now writing, they are coincident, which you can clearly see in the diagram here. Okay, so in this undeformed configuration, that is in the pre-buckling stage, there is no difference between the S that I have written here and the X that was otherwise present. Okay, so with this much of a little discussion, let us launch into the solution of this governing equation and let us see what answer it gives us when we use these boundary conditions. But please note that although these equations look simpler compared to the previously obtained approximate theory, there will be some challenges. Okay, and the first challenge that we have to deal with is that this governing differential equation that you see here, it is so this derivative term is certainly a linear term, but we do have the presence of a nonlinearity through the presence of this sine theta term, and that is going to throw up in a good challenge in front of us, but we'll deal with it, and we'll deal with it immediately. So we start out with this equation, ei d squared theta ds square plus p sine theta equal to 0. And the way we deal with this nonlinearity is with a standard trick which is used in all of mathematical modeling, in various areas of mathematical modeling, in quite varied areas actually. But we can have a discussion about that later. So what we do here is to multiply throughout by d theta ds. Okay, so it seems for no rhyme or reason that we're doing it, but you will see the beauty of this trick in just a while. Okay, so we just multiply throughout by d theta ds. So this is the real trick here to deal with this nonlinearity. Sorry about that. I'm miswriting this d theta ds. Okay, now you see what we can do is to rewrite this term in this fashion. You just take a moment to appreciate the beauty of what we just did. Okay, so what was present as a second order term, we have now represented it as in this form, dds of d theta ds whole square. So this is the derivative over this entire thing. Okay, and if you just simplify this, you will get back this thing. Okay, so what is the motivation behind this? You will see that in a moment. Okay, now what we are going to do is to write this term also as a derivative with respect to s. This is dds of minus cos theta. And I believe some of you have already figured out what is the motivation here. You see, in both these terms, we have managed to write it as we have managed to write them as DDS of something, DDS of something. Okay, so this is basically just asking for it for us to integrate it with respect to S. Okay, so if we do that, we integrate once with respect to S, then we obtain this here and this here, but we also end up with a constant of integration, a constant which we don't, of course, know. So our first job is to actually figure out something regarding this constant. Okay, so let us take stock of what we know and what we don't know. So maybe it is a good time to take a look at the boundary conditions that we have. So first of all, you note that this end is pinned and this end is also pinned, which means that we cannot say anything a priori regarding the slopes of this beam or this column at this end or either or this end. We do not know anything a priori about the slope. So all that we can say is that theta here at s equal to 0 and theta here at s equal to L, they are not specified. Okay, so we must conclude that at s equal to 0 and s equal to L, theta is not specified, which means we have to conclude that it must be true that at s equal to 0 and at s equal to L, ei d theta ds is equal to 0. All right, so since the ends at s equal to 0 and s equal to L are pinned, theta is not specified. Therefore, at s equal to 0 and s equal to L, we must have that ei d theta ds is equal to 0. Now this should immediately make us quite happy because we do have the presence of this d theta ds, and because you see our ultimate our goal here, our immediate goal here is to find this c, but even though we obtain this value of d theta ds, but we still don't know about this theta itself. Okay, and that is actually problematic because we have just now said that theta is not specified, so we don't know this theta, and unless we know this theta, we do not know this cos theta also. Now what can we do about it? Okay, so right now as things stand, we simply don't know how to deal with this unknown theta. The only thing that we can say, however, is that because this entire situation is symmetric at s equal to 0 and s equal to L, so if it buckles, it'll buckle like that. So the only thing that we can say regarding this theta is that it is going to have the same value at s equal to 0 and at s equal to L. Okay, but we don't know those values. Okay, so what we are going to do is we are going to just say that let it be some value alpha. Let the theta be equal to alpha at s equal to 0 and s equal to L. Sorry about that. Okay. All right. So the only thing that we can say is that that at s equal to 0, let theta be is equal to alpha. Please note that this alpha is not known. Therefore, what we can say at s equal to L is that theta should be equal to minus alpha. The reason we say that is if you consider this beam or rod and then you consider the deformation like this, then at s equal to 0, if you have this angle alpha, this angle, this is minus alpha. Okay, the magnitude remains alpha, but in terms of the algebraic sign, because you note that theta is one of our coordinate variables. Okay, so we have to be careful about the sign. So if you are calculating or if you are denoting the positivity of theta in this direction from this horizontal line in the anti-clockwise sense, so this angle that uh, uh, that should be minus alpha. Okay, now uh, now how do we use all of these things? Okay, so what we are going to do is to go back to the form that we had obtained here, and then write this thing at s equal to 0 and at s equal to L. So at s equal to 0, we have ei d theta ds square minus p cos alpha. Please note that this term is 0 at s equal to 0. So this is c. So c is equal to minus p cos alpha. Similarly, you do at s equal to L. This is again like this, but p cos minus alpha is simply p cos alpha because the positivity or negativity inside the cos doesn't matter. So from both of these, what we are obtaining, thankfully they are the same thing, we are obtaining that c is equal to minus p cos alpha. Therefore, what we conclude is that in general, all throughout the domain, as we had obtained earlier, it is going to be ei d theta ds cos whole square minus p cos theta, that is going to be equal to minus p cos alpha. Now let's see how we can simplify this. Let us not lose sight of the fact of what we are trying to achieve here. Okay, so our ultimate goal uh, is twofold. First of all, we do want to find out exactly like our previous approximate theory as to what the critical value of the load, the P, is such that buckling will be induced. That is certainly our first goal. But previously we had seen that in our approximate theory, even though we managed to find out the critical value of this P which would induce the buckling, but we could not say anything regarding the deflection itself. We could say that it was buckling, but as regards to its amplitude or how much the deflection was taking place, that remained an unknown, and we had said that that is a shortcoming of that theory. So because we are now dealing with a more exact theory, it is naturally our hope that it is going to give us something better. Okay, so let us try to see if we can indeed proceed towards something which would give us some estimate of the deflection. All right, but we have to traverse quite a bit before we can reach that stage. All right. Now you see, uh, after this stage has been reached, what we would like to do uh, is we have to take the square root of this thing. Okay, so let us do that. I think I missed a half all throughout. Yeah, so all throughout this, I missed a half. It did not matter here, although it should be present. But here it does matter, otherwise I'll get my coefficients wrong. Okay, so now this is twice P by EI cos theta. This should be cos alpha. All right, square root of that. Now the question is, because we are taking the square root, whether it should be positive or it should be negative. That is the question in front of us. So, so in an actual classroom environment, I actually spent some time asking the students this. So I would prefer if you just pause the video for a bit, because I'm just going to reveal the answer immediately here. Okay, so the answer is that this square root should come with a negative sign and not the positive sign, because you see this theta is actually starting out from this positive value of alpha. It is, the slope is going like that. Okay, so the curve is going like that, so the slope is actually decreasing, and you can see that at this midpoint the slope has actually become 0, and thereby it is becoming more and more negative until it reaches this value of minus alpha. So d theta ds, as we are traversing along S, is actually decreasing from alpha through 0 to minus alpha. Okay, so it is negative. So the reason that we point out here is that it is a negative sign because theta is decreasing from alpha to minus alpha through 0. All right, that is a crucial step. Now we'll do a bit of algebraic manipulation here. So let me just copy this step here and proceed in the next page. Sorry about that. I hope it works this time. All right. So this is simplified as, the right hand side is simplified as, we use a bit of trigonometric identity to write this as this cos theta as 1 minus 2 sine square theta by 2, and this cos alpha is 1 minus 2 sine square alpha by 2, so that overall what we are going to end up with is this thing. Twice sine square alpha by 2 minus twice cos square theta by 2, that is also under the square root, which basically means that this is just the 4p by EI. But what I'm going to do here is I'm going to consider or set it up in a fashion which will enable me to carry out an integration. Okay, so I'll write the ds, and then I am skipping a couple of steps here. So this actually will come in the denominator, but you please note that what I'm basically doing is kind of like ds is going that side, and this entire thing is going to the denominator here, and the d theta is present here, and this is left as sine square alpha by 2 minus, this should be sine. And this thing is under the square root. Let us not forget that. Okay, and we intend to carry out the integration here. So this ds integration with respect to s is going from 0 to L. Now this integration, you note that this theta is actually going from alpha to minus alpha as s is going from 0 to L. That is very important to note. Okay, so just because we are writing it like an integration, please do not be tempted to write it as minus alpha to alpha. Okay, so you have to write it corresponding to the limits of s that we have put here. So when s is equal to 0, on the right hand side you have theta equal to its value at s equal to 0, which is alpha, and when s equal to L, the theta is equal to minus alpha. Okay, so we can do a little bit of a simplification here, again exploiting the symmetry of this theta. So what we are going to do is, we note that this entire integration is going to be symmetric about theta equal to 0, which corresponds to this to the midpoint. So we leave this as it is, but on the right hand side, it's just a bit of a simplification. We write this as integration alpha to 0 d theta Please note that we can do this. So I must not forget to write this 2 here. I can do this because this here is a sine square theta by 2. So this is an even function. Okay, that's why I'm allowed to do this. So taking this entire integration from alpha to minus alpha is twice of alpha to 0. Okay, because whatever happens from alpha to 0 is the exact same thing that happens from 0 to minus alpha. Okay, now what this will give me, so this integration is simply L, and on the right hand side you note that this 2 cancels with the square root of 4. Okay, so what we end up with is this thing. So I'll leave this thing as it is. Okay, again, I wish to emphasize that our ultimate objective here, or at least our first objective here, is to find out the critical value of P which will induce buckling. Okay, so all our efforts, all these efforts are directed towards that goal. Now, there are some standard procedures to proceed from here. I say standard because the result that we'll end up with that has a certain very special form, in fact such a special form that it may look quite and I'll illustrate this to you, but I'm just telling you as a precursor that that final form has it will be complicated looking, but it has such a special form and such general utility in many areas of mathematical modeling and applied mathematics, is that in packages like symbolic Python, it is actually built in. So we can actually call those kinds of forms. So you'll see what I'm talking about. So what we do right now is we make the substitution. Okay, we make the substitution sine theta by 2 as k sine phi. Okay, now this might seem like completely alien to you, but you'll soon see, the motivation behind this. Okay, we make this substitution. Sine theta by 2 is equal to k sine phi, where k is equal to sine alpha by 2. Okay, like one may ask, like, why in the world would we do such a thing? So you just one motivation you can pick out here is that if we write it like this and we substitute it here, then this term is going to give us sine square alpha by 2, which is quite common with this, then multiplied by sine square phi. So it helps us to take out this sine square alpha by 2 as common. So that is one motivation. So let me write this down. Therefore, L is equal to minus EI by P. See, I have to be a little bit careful here, because when I make this substitution, this, and you see this limit here, or this integration here is with respect to theta. But when I make this substitution, I am going over from theta to phi. So it will be perhaps better if I, instead of writing down the next step with regards to the making the substitution, if I just write down what happens to this uh, to this term, to the d theta term. Okay, so from sine theta by 2 is equal to k sine phi. If I carry out one differentiation with respect to theta, what I'm going to get is this thing. All right, and on the right hand side, I'm going to get I am actually carrying out the differentiation of this entire thing with respect to phi. So it is as if we are getting a d theta d phi here, and on the right hand side will be just cos phi, and then I'm taking this d phi to this side. Okay, so again skipping a step here, but I'm sure you understand what just went on here. Okay, now that we have this, you see that I wish to make a substitution for this d theta also. So what is going to happen is that this d theta is going to be expressed so this 2 goes here, and this cos theta comes here, cos theta by 2 comes here. So if I make all of these substitutions, therefore making the substitutions, what we end up with is square root of ei by p from here. I'm not going to write down the limits just yet. For the d theta, I'm writing this as twice k cos phi divided by cos theta by 2, and then in the denominator what I have is sine square alpha by 2 minus sine square alpha by 2. Please note that this sine square alpha by 2 is basically coming from the substitution of this sine square theta. So this k square sine square phi, that k square I'm replacing by this thing sine square alpha by 2, and I end up with this sine square phi. Okay, and that thing is like this. Okay, Now, please note that it is important to figure out the limits of phi corresponding to the limits of theta. Okay, so when theta, so if you look at here, so when theta is equal to alpha, uh, this is sine alpha by 2, and k is also, so we can just figure it out here in our rough column, that uh, uh, theta is equal to alpha by, sorry, alpha, or theta equal to alpha, I will have sine alpha by 2. So I'm basically using this this equation here, k sine phi, but k itself is this sine alpha by 2, which means that sine phi is equal to 1, which means that phi is equal to pi by 2. Okay, so please don't be worried with the fact about the cyclic uh, values of this phi. We just want to have the base value here. Next, for theta is equal to 0, because you note that in the previous page, the limits that we're dealing with is theta going from alpha to 0. So we have theta is equal to 0 here for the upper limit. And for that, what we're going to get is this this sine 0 by 2 basically. So that's 0. And then we have this k sine phi, which basically means that phi is also equal to 0. So the limits for this integration with respect to the phi, because you note that I've forgotten to write this d phi here, since the entire integration is now with respect to phi, the limits also should be appropriately written for the phi. So they should be for going from this phi equal to pi by 2 to phi equal to 0, corresponding to theta equal to alpha going to theta equal to 0, which was what we had earlier. Now, a little bit of the simplification is definitely possible here, but only a little bit. uh, we have this cos phi here. We have this cos theta by 2 also here. Now, you see, this sine square alpha by 2, so that can come out as sine alpha by 2, and you see it's not such a bad situation here, because k is equal to sine alpha by 2, and we have a k in the numerator already present, and what is left here is this sine square phi. Okay, so what we have here is this thing, and we have this d phi here, 0. So I am going to immediately cancel this k with this sine alpha by 2. What we are left with is twice cos phi. Now this is 1 minus sine square phi, so that is cos square phi, but there is a square root here, so we end up with this cos phi also, so that will cancel with the numerator. But please don't forget that I have a cos theta by 2 here, and that cos theta by 2 now has to be written in terms of the k sine phi. Okay, so that will do in the next step. So therefore L is equal to minus EI Sorry about that. So this is 1 minus sine square theta by 2 okay, and that you see that sine theta by 2, we already have made a substitution here. Sine theta by 2 is equal to k sine phi. So this we can write ultimately as 1 minus k square sine square phi with the square root. All right. Now, let me just check if I've made any mistakes here. In going from this step to this step, let me just check from the beginning. All right. So, in going from this step to this step, I have missed this 2 here. Okay, this 2 here. So that should be very much present. Let me just bring it to this side. Okay, so this particular form, okay, this was what I was talking about earlier. You see this okay, I'll make another one last simplification. You see this is a minus here, and this integration has this weird looking limits. So let us make it a little bit aesthetically more pleasing by writing it like this. We just reverse the limits by absorbing this minus sign. Okay, so this particular form of the integration that we have ended up with, that is very weird looking. Okay, but the good news is that this weird looking form, it arises in a number of different fields. This was what I was telling you earlier. Okay, so it is so very common and so very important in applied mathematics and mathematical modeling, that it has actually been presented in a built-in form in packages like Symbolic Python and Mathematica. Okay, so what this is referred to as the complete elliptic integral of the first kind. In fact, these things are so very important that you'll find entire Wikipedia pages devoted to just this integration, believe it or not. So I encourage you to just do a Google search on this term. Okay, it is referred to as the complete elliptic integral of the first kind. Now, all that is fine, but as far as our goal of obtaining the critical value of P, where do we stand? Okay, so what we say here is that given a particular value of P, okay, given a particular value of P, what can we do about this integral? Okay, suppose we do know how to find out these values, the value of this integral using Symbolic Python or some numerical techniques or whatever, or Mathematica, whatever. Suppose we do know how to find out the value of this integral. Okay, but you see here this k This k is involving the alpha. And let us not forget that we don't know alpha. What do we know here? You see the left hand side of this equation. The length, that is very much known to us. The Young's modulus is known to us. We know the second moment of area. And suppose we are actually given a certain value of the applied load. So this P is also known to us. So in this entire equation, in the left hand side and the right hand side, considering them together, the only thing that we don't really know is this K. But we do know, or we have means of solving this integration for different values of K. So we now have an equation, a complicated equation for which we have to put in some effort, but we do have the means to find out the value of K given a certain value of P. Okay, now why is that good news? It is good news because the moment we have a value of K which satisfies this equation, we can immediately say that we know the value of that unknown alpha which has been bugging us from the very beginning. Okay, so we have accepted and acknowledged our ignorance about our alpha, but we have not gotten rid of it. Okay, because it is very much present within this scale. So what we can do now is that we can say that given a value of P, we can find a value of K. Okay, value of K. So let's say that this equation is such that this equation numbered hash is satisfied, and the moment we have such a thing, we can say that we can find, so basically we can find the value of alpha because K is equal to sine alpha by 2. All right, then what about the question about finding the critical value of P? Okay, so let's just carry on this video a little bit longer and take a look at what we can do after we have found out this value of K. Okay, so or if you can do a little bit of a simplification. So let's go to the next slide and write this thing again. Okay, so L is equal to twice square root of EI by P integration 0 to pi by 2 d phi one minus K square sine square phi under the square root. Now we can write this as the L square by EI. We've just taken this term here and this term's also here in this fashion. And then we write it in this way, pi square EI by L square. The motivation of suddenly bringing about this term here in the denominator, okay, through the introduction of this pi square, is that we know that this particular thing is nothing but the Euler buckling load. This pi square EI by L square, this is the Euler buckling load. Okay, so you see that because I have introduced this basically the 1 by square root of pi square here, I will have to compensate by writing this pi on the right hand side also. But the good thing about this situation is that we have now in our hand an estimate of this P in terms of the ratio with the Euler buckling load. So this is P by P Euler, okay, because that is what this particular combination is. So suppose you rethink about this problem in the sense that you know the value of this ratio P by P Euler, then which is equivalent to saying that you know the value of P, then you can find the value of K to find the value of alpha. And once we know the value of alpha, we are going to show how we can proceed towards finding the deflected shape of the beam. All right, so that is the second part of the solution, which we are going to look into in the next video. So already this video has become quite long, so I'll end it here and continue from here in the next video. Thank you very much.